Okay, here we are at the end of week 11, module 9, and we're starting chapter 5. So in this chapter, we're kind of finishing up looking at differentiation, and we're going to kind of do all the things that you do in a standard differentiation course. Okay, so the goal here is we want to be able to differentiate any function. Okay, well, we can do that numerically, right? We can just do rise over run, but we want formulas. So derivative formulas, basically, there are two kinds. Firstly, there's your derivatives of basic functions, sort of the building blocks of functions. And so here is the list of derivatives that you know. And, like, for example, the derivative of a straight line is just the slope. We've got the power law, the derivatives of log, sine, cosine. Okay. So, last module, I asked you what was the antiderivative of the constant m. This time, the first module question is, what is the derivative of the constant m? The other type of derivative law is how you then take the derivative of basic functions put together. So most of these you've seen. There's two new ones. So we know, for example, the derivative of the sum is the sum of the derivatives. And that's true also for the difference and constant multiples. The two new rules are the product rule. So the derivative of a product is, so the derivative of fg is f prime times g plus g prime times f. And the next slide we'll see why that's so. The most complicated rule is the quotient rule. So the derivative of f divided by g is this complicated formula. The way that I remember is that the top is low d high minus high d low. So low d high means the low, the denominator, g, times the derivative of the top, which is f. So g times f prime minus high d low, f times g prime. And then that's all divided by g squared. Okay, we'll look at some examples of those and hopefully that'll be clear. And then the other rule we've done, way of combining functions, is composition. And that's the chain rule. And so the derivative of g of f of x is just the product of the derivatives. So it's g prime times f prime. It's f prime at x because f is the x goes to f, and then f of x goes to g. So that's why it's g prime of f of x. Okay, so the other module question is find the derivative of x squared in two ways. So the easy way is just to use the power rule, and that should be really straightforward. But you notice that x squared is the product of two functions, x times x. So do the product rule and just verify that you get the same answer as the power rule. Okay, so this is the reason why the product rule works. So we're looking at the derivative of f times g. So we think of area as f times g. So f is some width and g is the height of the rectangle. And then we look at how the area changes as f and g changes. Okay, so along one side, you're going to have a little rectangle, which is going to be the change in f times g. And you're going to have another little rectangle, which is f times the change in g. And then as well, you're going to have a really tiny rectangle, which is the change in f times the change in g. And so that's the change in f times g. So if we divide that by delta x, we'll get the derivative, right? So delta f times g divided by delta x gives us f prime times g. F times delta g divided by delta x gives us f times g prime. And then if we've got delta f times delta g, both of those are really tiny, right? So if you multiply them together, they become infinitesimal, and so you can disregard. And that's the way that I think of the product rule. Okay, so here's some examples of using those new rules. Okay, so first a few product rule examples. So let's say we've got x times sine. Well, the derivative of that is, well, first we take the derivative of x, which is 1, we multiply by sine x. And we add to that x times the derivative of sine, which is cosine, and so we end up with sine x plus x cosine x. Let's take the derivative of cosine times e to the 2x. Okay, first we take the derivative of cosine, which is minus sine, and we multiply that by e to the 2x. Then we add to that cosine of x times the derivative of e to the 2x, which is 2 times e to the 2x. And that's it. So that's a good enough answer. Sometimes you've got to do a little bit of tidying up of the answer. Like, for example, the next one, we've got x times ln of x. So the derivative of x is 1. So we take 1 times ln of x plus x times the derivative of ln of x, which is 1 on x. X times 1 of x is 1. And so this has another extra step. We get the derivative being ln of x plus 1. Okay, let's have a look at the quotient rule. And these can get quite complicated. And so you try and avoid doing too much extra work, right? So here we've got in number 4, we've got two polynomials, one divided by the other. Okay, so again, we do low d high. So we get the derivative of x squared plus 1 is 2x. And then we subtract high d low. And the derivative of 2x cubed plus 2 is 6x squared. Okay, so we can do a little bit of multiplying out. And we see that we've got 4x to the 4th minus 6x to the 4th, so those cancel out. And so we're left with minus 2x 4th minus 6x squared plus 4x, and that's enough. With the denominator, don't multiply out the denominator, just leave it as it is. Okay. And finally, we've got, let's prove that the derivative of tan is secant squared. Okay, so tan is sine divided by cosine, so that's a quotient. So we take the derivative of that, we do low d high, which is cosine times cosine, minus high d low. So the derivative of the low is minus sine times sine. So we get cosine squared plus sine squared. And if you remember your trig, you should remember that that is 1. So we get 1 divided by cosine squared. That's a good enough answer, but if you do remember your trig, you know that 1 over cosine is secant, and so you get sec squared. Okay. Let's do a couple of word problems. Okay, let's have a look at energy consumption. So let's say that per capita yearly energy consumption C is 800,000 BTUs per person. So BTU is a British thermal unit. It's some measure of energy. And let's say, you know, there's some good green efforts to cut down on the usage of energy. And let's say C is falling at the rate of 1,000 BTUs per person per year. Okay, but on the other hand, the population, let's say it's 200 million, let's say it's rising at the rate of 1 million people per year. And so the effect on overall energy consumption is you've got energy per person going down, but the number of people going up. So is the total energy consumption rising or falling? Well, since it's a product, we can use the product rule and we can figure that out. So by the product rule, the derivative of energy is consumption times the derivative of population plus the derivative of consumption times population. And so we plug in the numbers that we're given there. And so we see that the effect of the population rising is to add 800 billion BTUs per year. The effect of the energy conservation efforts is to drop energy consumption by 200 billion BTUs per year. So overall, energy consumption is going up 600 billion BTUs per year. So the energy consumption is rising. So the population increase is overpowering the energy conservation efforts. Okay, another problem. Okay, so let's consider the Colorado River. So if you've ever been to the Grand Canyon, you've seen the Colorado River. It also flows to the Gulf of California in Baja, California in Mexico. And by the time it gets to the ocean, actually, it's the water's gone. Okay, the farmers use it. There's all these dams, and the problem with dams is that you then have this big water surface area, and water is then lost just to water evaporating. And so let's have a little investigation of this. Okay, let's say we have a river that was recently dammed, and we look at our river, and let's just say the lake is a rectangle, and now it's 50 yards wide and 950 yards long, and let's say it's getting wider at the constant rate of 3 yards per week and getting longer at the constant rate of 15 yards per week. Okay, so what is the current rate at which the surface of the lake is growing? Well, area is width times length. So the derivative of area is width times the derivative of length plus the derivative of width times length. So we plug in our numbers and we see that it's growing at 3,300 square yards per week. Okay, so we can make a formula for the area because the width starts out at 50, it's adding 3 per week, so it's 50 plus 3t. The length is 950 plus 15t because it's growing at 15 yards per week. We multiply those together and we get a nice quadratic. Okay, so we don't have to use the product rule for this. We can just use the derivative of polynomial. And we see the derivative of a is actually 3,300 plus 90t. So that's another, we've double checked then that the derivative at the start is 3,300 square yards per week. But we see actually that the growth rate is increasing, right? Because we're adding that 90t. So for example, after 20 weeks, it's growing at 4,200 square yards per week, right? The reason for that is it's getting wider and longer. So any increase in length and width now give a bigger increase in area because we're multiplying by those bigger widths and lengths. Okay, so this is actually section 5.2 of the text, and I want you to finish this off with questions 5 and 6, where we take into account water evaporation and we see what happens. Okay, that's us for this module.